Welcome to the course on computer design of electrical machines. We will have a lecture for today on transformer design as a part 1. Well, we like to of course have an outline of the lecture today with the introduction to the transformer design, then transformer classification and specification, construction and manufacturing process, then transformer design and constraints, followed by exercise, numerical problems and references like. So coming to the introduction to the transformer design, the transformers are used well in electrical energy systems, starting from typically from generation, because the transformer is the backbone for AC system. And the AC system won over the DC system because of only of the transformer, and that transformer allow us to generate at optimum voltage, transmit at optimum voltage, then distribute at optimum voltage and utilize at optimum voltage. So you can just see how at the generation we have the voltage, and then we step up at the generating station with the help of transformer. By step up transformer to transmission system. Then we have a transmission. Of course, we call it like auto transformer is just for the tappings, and then we of course at the distribution side, either it is you can call it primary distribution or secondary distribution. We have like a step down transformer to bring the voltage to at lower voltage level. So you can call it at the generation at optimum voltage means we cannot design the machine of very high voltage because of insulation and other constraints, but we can certainly transmit at very high voltage, which reduces the losses as well as the cost of transmission line. Apart from in distribution, again the equipment which we are utilizing in distribution system or finally in utilization, they are also of low voltage, of course, because of the several constraint and requirement. So we have to reduce the voltage to down. So there also we use this transformer. We call it step down transformer, or we call distribution transformer. On power system side, a type of transformer, we call it like a power transformer, and the transformer which utilize at the distribution side, we call it distribution transformers. Apart from this, step up and step down. Like, well, there are several standards on the transformer, starting from IEEE standard C57.12 in 2010 for general requirement of liquid immersed distribution power regulating transformer. Then other standard related to typically safety standard with the single phase and tap changing transformer. Then we have another standard with the standard code for liquid immersed distribution power regulating transformers, and then NEMA standard for typically of transformer and regulator and reactors like. So now coming to typical some application of transformer with this, some of the photograph you can just see. Here we have a transformer, use power transformers which are at generating station to step up the voltage from a optimum voltage, or you can call it low voltage of not more than typically of going to be 11 to 13 kV maximum to typically order of around either 220 or 440 kV or even 750 kV for the purpose of transmission. I already mentioned at high voltage, the transmission line have a lower losses as well as the cost of transmission lines reduces because the size of conductor reduces because of the low current like. So we use the power transformer normally at generating stations, power generating stations. Then we have these are kind of, you can see how the network is there for step up. So we have a generator, whether it is you can say different generator, whether hydro generator, thermal generator, or even including like now wind generation. In all cases, we use this transformer on power to step up like or so. Then we have a typically distribution transformer which are used at the utilization level to bring down the voltage for the equipment voltage. Of course, in different countries we follow the different standards and different voltage. Like especially this part of continent, we use like a distribution single phase 220 volt or 230 volt, and three phase we use normally typically 415 volt order of that. Of course, transformer at the secondary we have 433 volt in three phase. So we use the step down this voltage for the equipment as you see the photograph of distribution transformer. So coming to with this, so transformers are a static electromagnetic device with two or more windings and a common magnetic circuit, and they are one of the primary power apparatus used in power network. And the transformer change the AC voltage and the associated current from one level to another level, maintained to power balance between the input and output side without change of frequency. And the transformers perform AC transformation rather than the energy conversion from one or more side to circuits to another secondary side of circuit. So the main parts of the transformers are like a core which is made of ferromagnetic material, then yoke, also ferromagnetic material, and then the windings. You may have several windings, of course, maybe a primary, secondary, and tertiary winding, or multiple winding in the transformer on the same core. to transfer the energy from primary side to the secondary side or many secondary like. So, well, when the MVA rating is high of the transformer in case of above part, transformer equipped with the bushing and coolant conservator for effective cooling as well as to provide the enough, you can call it the protection for the voltage, high voltage like. So, you have a different, you can just see here the main parts of the transformer, I mean, where you have a typically the, in the oil filled transformer here, we have a cooling air, cooling oil of the transformer in the body, but of course you have a core and you have a primary and secondary of the transformer with the tank. And then of course, because if you go further higher rating, you have a more the losses. So to take care this losses, certainly you have a separate tank also, as well as you have a several means of cooling uh, with the typically with the not only oil but the circulation of oil in the tube as well as in the other tank. And then of course you have a protection system as you have seen here, like a with the conservator like, I mean, also. So well, these are the typically parts as you I mentioned it, core with the which is normally cold grain oriented steel. Today earlier we were using hot rolled grain oriented. There of course the losses were more than the cost and size was the more. Now we start using the cold grain oriented where we can give higher flux density in the core and yoke, and we are able to reduce the size of the core and yoke. Similarly, of course, we have a winding. Normally, we use the copper, but of course, in low rating transformer, especially distribution transformer, government have a restriction. We use only the aluminum uh, conductors in place of copper conductor because of the one of the major reason the cost like, I mean, also. Then of course the bushing which made from polymer and porcelain, and the coolant which is made of steel like. So you can just see again the different main parts of the transformer here, starting from as you see the cross section here, you have a typically the core. Closer to the core is the low voltage winding, and then we have a high voltage winding after the insulation, so that the cost of insulation is reduced. And then of course we have a yoke, then we have a core surrounded by winding, we have a winding, then we have a bushing, and we have a coolant conservators like. So you can have a basic parts here. We can say it's a core with the yoke, upper and lower portion called yoke, and both side limb we call it core. And we have a primary and secondary. This is symbolic diagram where the flux is linking both the winding, but practically we are not putting primary and secondary on separate limb. We are putting half the winding on both the limb. So you have a like a typically lot of transformer for high frequency applications, like typically used in the power electronics and electronics transformer, which normally made because of high frequency with the ferrite core, not with the typically the laminated steel, because these are of course low. I mean, power is also low. Apart from that, we go for high frequency. The size of the transformer reduced because of high frequency for the same amount of power. There are plenty of applications of this, and day by day applications are increasing of such high frequency transformer, and people are able to, like typically even if you talk about all these transformer in the like LED lighting, if some of the applications you talk about, and most of the power supplies, I mean, like typically it is more power converter supply, including whether it is a power supply of your computers, laptop, or if, even if it is the power supply, or even in many other applications of like welding. I mean, new application also emerge like a kind of welding and other, even for many electronics equipment, as well as typically in case of your power electronics application for the purpose of isolations for gate drive and other applications. So there we are using this all high frequency transformer for the many purpose of this transformer is one is the isolation, the another is that to get a many output voltage so that we can convert into many DC isolated supply, even use like typical example with the computer power supply that you need power supply for cooling fan, you need the power supply for motors of floppy disk drive, hard disk drive, you need the power supply for your processor. So all these DC supplies are isolated and they are of different voltage. So you have a, I mean, in the transformer several secondaries which give you different voltage, where you keep different number of turns like also. Well, you have a large transformer at typically power plant we talk about. Then you have a typically a electric arc furnace transformer. I mean, in the furnaces, of course, we have to convert the three-phase supply typically to single-phase supply, and we use a special connection like typically what we call it like a Scott connection, which convert three-phase supply into two single-phase supply, and we give two separate furnaces so that these furnaces behave as a balanced load on the three-phase supply system. Since these are very high power rating, order of 500 to 600 kV up to that maximum rating, or even lower than that, so such large load we can single phase load we cannot connect directly to the three-phase supply system. So certainly we have a special arrangement of these furnace transformer for the purpose of this. The purpose of those transformers is number one, isolation, and number two, to convert this supply from three-phase to the single phase. But when you have both the furnaces have a almost equal load, it behave as a balanced load on the three-phase supply system through this transformer arrangement. Of course, there are these transformers, similar transformers we use like in rectifier for many applications, including the HVDC, and typically even for variable frequency drive to convert many number of phases. Transformer can convert the three phase to any number of phases, starting from two phase. Of course, three phase to three phase is already there. You can convert four phase, five phase, six phase, or any number of phases. People have gone as high as maybe 19 phases to get a 38 pulse for typically for naval applications where the harmonics required is less than 3%. So there are also transformer. The very purpose is to not only the isolation but providing the phase conversion also, and providing phase shift also with the help of transformer. So there are plenty of applications of this transformer in those applications well, of course, we have a plain transformers which we use on PCB for electronics applications. They certainly give a very efficient design because conductor we cannot keep like a larger cross section area. We keep the conductor cross section area as a kind of, you can just see kind of a kind of foil, which reduces eddy current losses in the conductor in a high frequency transformer. So we use certainly planar transformer on which we mount on the normally PCB of these electronic circuit you can see like a pulse transformer on PCB. Then you have a typically different outdoor transformers which are used in your company, typically electronics, typically your all the amplifiers, sound amplifiers, which you use in a transformer, which is normally used for frequency. This is the interesting application for which you call it the impedance transfer using transformers. What we do here, we might have probably the mic or speaker of around 10 watt, hardly keeping about only 3 ohms, 5 to 10 ohms, which get reflected 5 to 10 kilo ohm on the amplifier. So that amplifier is not loaded. The transformer transfer the impedance, this impedance with the help of turns ratio square, because if you really transfer the secondary impedance to the primary side, it's multiplied turns ratio square. So if you have a typically turns ratio even let's say 100, so it will give your transfer ratio about 10 to the power 4. So it means your 1 ohm will get to 10 kilo ohm on the primary side of the 1 ohm secondary. So that kind of the transformer we use in electronic circuit, so that amplifier is not loaded. The power associated is not very high, but more importantly that normally your speaker mic, they run with the low power, hardly 10 to 15 watt or 20 watt, or you might have seen that 50 watt amplifier is my speaker is very high, sound, or you can say speech, but is hardly have a very low power with the low resistance that transferred on amplifier on high impedance, so that the amplifier is not loaded. So you have typically the circuit symbol for transformer with the transformer with 2 winding with the ferromagnetic core. Then you have a transformer with 3 windings, and the dot shows the relative configuration of the winding polarity, and transformer with the electrostatic screen preventing the capacitive coupling between the winding. In many applications, this is required to reduce it. And in case of even isolation transformer. So well, with this we can of course classify the transformers. So we classify the transformers basically on the basis of core, that how the core construction is there. So we have a 2 type, core type and cell type. And the second classification on the based on transformer ratio, we can call it like a step up or step down. And the third is based on the service, like a distribution transformer and like a power transformer. Many other applications also which can be classified based on the service. So we have a classification of transformer on the basis like voltage ratio, construction, application, number of phases. This is another way of classification. So we can think about like a step up. Transformer means the transformer increases the voltage from primary low voltage to high voltage. So you certainly have if it is a low voltage in the primary, you have a less number of turns, as you can see here, and in the secondary you have a higher number of turns to increase the voltage to the higher. So this is all symbolic diagram. Otherwise, which I already mentioned it, it's not that primary is put on first limb and secondary is put on second limb. It's the half the winding on primary, half the winding on the secondary put on the same limb, and low voltage winding is closer to the core and the high voltage is kept away from the core. So similarly, this step down transformer which is used normally in distribution system or many other applications. So here certainly primary will have higher number of turns because of high voltage, and secondary have a low voltage and certainly have a less number of turns. So you have a typically a different kind of transformer. If you really have a typically look into the type of single phase transformer, here you have with the cell type of transformer. I mean, if you have a top like with the 3 legs and one wound, 2 return legs, and legs and yokes are not of equal construction because of the different flux density you can maintain in the, but flux will be of course uh, is half in the yoke as well as the side limb. Then you have another transformer which we call it like a with the only the 2 legs, which we call it core type of transformer for single phase, and you put certainly winding and prime first as well as second yoke or limb, which we call it yoke core, and upper portion lower portion we call it yoke. Then this is we have a 3 phase, typically another transformer of 3 phase, where we have a in the first case only 3 limbs, and this called 3 phase core transformer, core type of transformer 3 phase. So all the 3 limbs have a 3 phase winding. Of course, primary and secondary of the each phase is put on each limb. And the second case we have a cell type of transformer with the 5 legs, and the inner 3 legs keep the 3 winding. So there is a reason why we have a cell type core type. Cell type winding we can adjust the leakage reactance by adjusting the winding layers typically in cell kind of transformer. So these of course cross section are there and they have a relative merits and demerits, and they are used for in different applications with different objective and purposes like. So this is typically 3 phase cell type of transformer, as you can see here with the 5 and but 3 uh, windings are put on 3 central limbs like with the 5 legs. So you can call it starting with the core type of transformer. So you have a single phase core type and 3 phase core type, where in single phase you have a 2 winding on 2 side of core, and 3 phase you have all the 3 limbs you have a 3 phase windings. So this we call it the core type of construction. So the low voltage winding is wound inside near the core, as I already mentioned earlier. The high voltage winding is wound outside and circling the low voltage winding away from the core to avoid the, to reduce the insulation. Um, you can call it the thickness of insulation or type of insulation. So reason for this winding arrangement is the quantity of insulation material required is less, and in order to have reduced leakage reactance, 2 windings can be coupled together tightly with each limb carrying 1/2 of the primary and secondary on the same limb. This is already mentioned in many times. Because it becomes very important, because in symbolic diagram we always show, one winding is on one limb, another winding, but this is reality that we put half winding on the both the limbs of even of single phase. So as you can see here, the LV winding is put on the one closer to the core, and HV winding, half the HV winding is put away from the core to reduce the, you can call it the insulating material. Also, and of course the flux path is, you can say, through the core. That core we call it both sides of the limb, and upper and lower portion we call the yoke here. So we have a cell type of transformer single phase, where we put a primary and secondary both on central limb in single phase, and 3 phase also we have a 3 limb of 2 type of construction. There is one type of construction, there is another cell type of construction that we put all the 3 windings on central limb in even in case of 3 phase. So the cell type transformer, the primary and secondary windings are placed together alternately, giving rise to a sandwich type of winding with a high voltage winding sandwich between the low voltage winding, and central limb carrying the total mutual flux, while the other limbs carry half the total flux. This creates the double magnetic circuit. And this is a typical, what we mentioned it. You have LV closer to a yoke, and then you have LV, and we put the winding in sandwich form, which by which we can adjust the leakage reactance required to be in many applications that you have to adjust. Sometimes the leakage reactance too lower, sorry, like in case of distribution transformer, and you have to sometimes increase the leakage reactance in case of power transformer to limit the short circuit current level. So this is typically the example how you really have this 3-phase cell type of transformer. So we have winding only on central limb, primary as well as secondary, both on the same, and put the coil of sandwich type of construction like. And this is the comparison typically of core type and cell type of transformer, which we mentioned it, that the core type of course encircled by the winding, and of course cell type is more complex, and core encircle the maximum parts of the winding. So number of magnetic circuit of course is single in case of core type, and cell type there are 2 magnetic circuit from both side of the, you can call it the yoke portion, and number of limbs for, in case of single phase there are 2 limbs, in case of core type, and cell type there are 3 limbs. Type of coil preferred of course is cylindrical in case core type, and in case of typically Cell type, we prefer to multi-layer disc or sandwich type, by which we can adjust the leakage reactances. And leakage reactance and possibility of reduction comparatively high and cannot be reduced, but comparatively low and can be reduced in case of cell type transformer. Maintenance and repair, easy to maintain and to repair as a winding in case of core type. In cell type difficult to maintain and repair, and for dismelting, a large number of laminations are to be removed. And cooling and heating dissipation, effective due to distribution of winding, and difficult in cell type due to core cannot be effectively cooled rather than the winding where the more heat is produced. And electromagnetic forces and circuit, of course core type it is large, but in case of cell type it is small because winding is well embraced by the core. And application is suitable for high voltage application, this core type, and cell type suitable for low voltage and medium voltage application. So this give a typically the features of two type of construction, core type and cell type of transformer. Now coming to typically based on application, that the distribution transformer is used for stepping down the transmission voltage to distribution level or stepping down the distribution voltage to standard voltage as per the service requirement of industrial and commercial load. The rating of transformer is usually here less than 250 kVA, and the type of connection used is 3-phase 4-wire delta star, and secondary is made particularly star connection to provide the neutral terminal for the single phase distribution. Of course, because of this reason we have to keep primary in delta, otherwise on high voltage side we normally prefer to have a star connection, but here we have a delta connection so that it provides the path for the circulation of your harmonious current, and that provides the stable neutral for the secondary of isolated secondary of the 4-wire system. So the period of the operation of the distribution transformer is 24 hours throughout the day, because you have to give the supply to the consumer throughout the 24 hours, and as the design should be done in a way such that the efficiency is maximum even at half the load condition or even 75% the load, because you will be keeping leading to a good all day efficiency. Like the flux density usually less than 1.7 Weber per meter square. Ratio of iron to copper loss is normally typically 1 to 3. Here because we design at typically of less than full load, so certainly we say we have to reduce the iron losses here. As this type of transformer is located in the vicinity of the load, the voltage regulation must be good, so which can satisfy all the by having a small leakage reactance which we can adjust by cell type of transformer. So then another features of distribution transformer, usually the percentage impedance is in the range of 4 to typically offered around 18%. The voltage regulation in the range of 4 to 9%, and typical type of cooling is self-oil cooling. Might have seen the distribution transformer in the vicinity, how it is mounted on the poles of 3-phase transformer and single-phase transformers. It depends in the different part of the country how this transformer are made. Like North America, you will just see they have a transformer of single-phase distribution transformer. We normally here in India we have a 3-phase distribution transformer on the pole. So coming to the now power transformer, the ratio of iron loss to copper loss is usually 1 to 1. Or you can call it the maximum efficiency at the full load, and that is the main reason is that they all the time runs at full load because they are at generating station. So you switch on, you bring the transformer into service when it is fully loaded. If you want additional, when additional generation by another generator is there, then you can bring another transformer in operation. So, but the transformer is preferred to be operated all the time at full load, and that's why the efficiency is at full load the maximum. The voltage regulation is not an important factor, as this transformer is not located in the vicinity of the load, and the leakage reactance can be made high, used for limiting the short circuit current, and as well as the electromagnetic forces under short circuit fault, leading to the less mechanical forces. Usually the percentage impedance is the range of 6 to 18%, so voltage regulation in the range of 6 to 10, and the type of cooling used is force air or force oil cooling. So this typical photograph of the power transformer you can just see, because rating is substantially high. Now coming to the classification on based on number of phases, you can have a single phase transformer. So this type of transformer has a single phase primary and single phase secondary placed with either core or cell type of construction, and it is used for low power application. And this 3-phase transformer, this type of transformer has a 3-phase primary and 3-phase secondary placed with either core or cell type of construction, and it is used for high power application. The 3-phase transformer can be made by connecting 3 single-phase transformer also into a 3-phase transformer bank, or can be inherently constructed 3-phase transformer with a common magnetic circuit with all the 3 phases. Well, you can have here 3-phase transformer bank consisting 3 single-phase transformer or 3-phase transformer a comparison. So first is the cost. Cost is large due to the large volume of three single phase transformer, and three phase unit is certainly cheaper and smaller in volume. Efficiency certainly is less for three single phase unit compared to three phase one being a unit, one unit efficiency is high, and installation maintenance is little higher in case of three single phase transformer compared to the three phase transformer, which is easy, and fault recurrence easy to service. Of course, you can take single phase unit out and take another to replace, and so of course, if difficult to service in case of three phase one unit like. So typical example, you can have a three phase transformer here, winding, primary winding and secondary winding, and of course you have a tertiary winding as a stabilizing tertiary winding also. So many cases we have a tertiary winding also in large number of transformer for many purpose. I mean, one may be in case of the providing a compensation, another is stabilizing. So there are plenty of applications for which we use the sometimes tertiary winding also in three phase transformer. So in this three phase transformer, the reason for the use of tertiary winding are as follows: ability to supply an additional load with a small voltage different from primary and secondary, like an typical example at generating station. I mean, your generation voltage itself is quite high, maybe 11 or 13.6, and even secondary is much higher, but the load are certainly of low voltage. I mean, maybe three phase 415 volt or maybe single phase of 220 volts. So to get, you just normally have a tertiary winding for that purpose. To provide the voltage for compensating capacitors for power factor correction at a different voltage or at optimum voltage, at even in distribution or transmission transformer, as stabilizing winding for limiting short circuit or fault current when connected in delta, for indicating voltage level in testing transformer used for high voltage, and to reduce zero sequence impedance, making easy to flow fault current, easy to ground. So this is, you can see how it is the LV winding plays with the core in case of these, I mean, transform medium voltage, high voltage or low voltage winding arrangement in three phase transformer. So transformer specifications are their rating and performance expectation. A designer needs to know the following important specification with regard to the design of transformer: rating, capacity and output kVA, and voltage rating is voltage rating of HV and LV winding with or without tap changer and tapping, and of course the frequency, number of phases, maybe one or three, type of winding connection like maybe star star, star delta, delta delta, delta star, with or without ground, or maybe polygon, hexagon, Scott, zigzag, T connection. There are plenty of connections, 7 to 8 connections where three phase transformers are connected for different applications, different purpose. Then rating, continuous or short time rating, and then the cooling, whether natural or forced cooling, with the only with the air or with the oil or with the forced air or forced oil, and type of core transformer can be classified as core or cell type or power or distribution, or even many electronics transformer. There are plenty of classification of this type of transformer. Then efficiency as per the impedance location, like indoor or platform mounting, and temperature as permitted also. And this is the typically the, you can call it nameplate rating of 100 kVA transformer manufactured by ABB. I mean, you have a like a typically the tappings also. How much is the tapping voltage? Voltage provided different tappings. What is the your load losses? What is no load losses? What is total mass? The mass effective. So even you can calculate the efficiency which standard it is following. I mean, like, so all the data and what is the typically the tapping voltage permitted and what is the voltage permitted, like number of phases, all the data, and of course the type of cooling, all those things are mentioned here, like in the nameplate specification of the winding. Now coming to the construction and manufacturing process of the transformer. So of course, as we know, as a construction, that we have a raw material as a core, then we assemble the core. So raw material as a, then from the coil we have a coil assembly, then we put a core and coil assembly. On other side we have a transformer tank, and we have a painting and finishing, and then we put core and coil assembly into the tank. Then we have inspection and testing, and then dispatch for and manufacture for energy efficient power transformer. These are the steps, like you can say how it is the core stacking system of the transformer, then how it is the typically you can call it like core cutting area, then how we have a core assembly, how we have a now coil winding of high voltage winding like a disc inner and outer cross section, how a coil winding for LV winding with the epoxy bonded and netting tape, then how we have a toroidal transformer winding. I mean, a special machine is there for toroidal transformer, how is a small power transformer winding and insulation insertion, then how we put a typically a carpentry section for wood for insulation in place, coil camping rings and coil support platform, then how we have a core coil assembly, then how we have a typically insulation section with wood used for insulation coil clamping rings and coil support platform, then how we really have a tapping arrangement of this primary and secondary coming out, and then how we have a inspection in process with the different testing, and then how we do the testing of these transformers. And then of course we have insulation coordination standard, basic insulation level tested with lighting impulse of 1.2 to 50 millisecond, forward, and you can call it front wave and your counter wave, and switching insulation level, switching pulse, and then induced voltage, and then applied voltage. So this is something insulation related to insulation coordination with the how as a withstand voltage we call it bill, basic insulation level, and of course on what is the impact on design about the bushing, lead structure, its clearances, winding clearances, stresses, and ground neutral point insulation. Then we have in SIL called switch insulation level, the external clearances, low lead clearances, phase to phase stresses, and then we have induced voltage, internal winding stresses, stress to ground, phase to phase stress, and applied voltage, that is stress to ground winding and leads. Like so, now we have a cooling methods as I have already mentioned. So we have a different kind of cooling. For cooling for medium transformer, we have air cooling, we have oil cooling, then we have a PLN leveling cooling with the synthetic fluid, and then we have a water cooling with the W. And cooling mode is that natural cooling, that's we call it our force cooling, or we have a direct cooling, direct oil flow. So you can think about different cooling methods. They are denoted with different letters and with the description. So we have internal cooling and external cooling. So first letter goes to the cooling medium, OKL, whether liquid with a flash less than 300 centigrade or liquid with flash point greater than 300 or liquid with no measured flash point. And the second letter is for N and F and D, that is natural convection through cooling equipment and windings, or forced circulation through cooling equipment, natural convection and winding, and D, forced circulation through cooling equipment, direct flow in the main winding. And external, of course, cooling is the third letter for cooling medium, that's A for air, W for water, and fourth letter is for cooling medium is N for natural and F for forced. So this is the description is given for the cooling notation, with these different letters for internal and external cooling, with the starting from first letter, second letter, third letter, and fourth letter, like how a cooling is defined in case of nomenclature. So you have a just like as ON, we already defined what is that you are. So you say here oil with the natural convection, and typical external cooling is by air, internal cooling by oil. So it's a natural convection. So similarly for all different kind of cooling, all these conventions are given for. Now coming to overload and life expectancy. The overload capacity is limited by oil and hot spot temperature, and probability of failure is high when the tensile strength of paper is reduced by 80%, and degree of polarization is also an indication of end of life, and loss of life with the hot spot temperature exceed 120 degrees Celsius, and rate of loss of life is double for every 8 degree over the 120 degree, and 3, there is a gain of life when manufacturing temperature is less than 120 degree, and check for 24 period if there is any additional loss of life for any specified load cycle, because sometimes load cycle is also changing a lot on the transformer. Well, sound level, that's also according to ANSI standard, so produced by magnetic structures in the core caused by varying magnetic flux, and fundamental frequency is a double power frequency 100 or 20 Hz for 50 or 60 Hz supply, and sound level energized unit depends on core material, magnetic flux density in the core, and core weight, because of core weight is higher for higher power rating, and sound level increases proportional to the log of MVA, and tank design and cooling system, and type of fans and pumps used in the for the purpose of cooling. Now coming to transformer design and typically the constraints. So design of transformer can be split into following main 4 steps: determining the output equation relating output of the transformer dimensions, determining the overall dimensions, design of cooling apparatus, and estimation of quantities such as no load current, current losses, resistance, and leakage reactance, and so on. So as a objective of the output equation is relates your transformer power rating to its dimension rating, and typical example of output equation of a single phase transformer is Q. Normally rating of the transformer is always in VA or KVA or MVA. The reason being that you don't know what is the power factor of the load I mean, by which transformer can be loaded. It can be loaded only by reactive load, maybe only by capacitor, a bank, or it can be by reactors, or it can be by your active load like motors or others. Like, so that's the reason we don't know nature of the load by which transformer is loaded. So that's why we load rate in terms of VA, kVA or MVA. So here Q in kVA will be Vp IP, I mean primary voltage and second primary current into 10 power 3, or secondary voltage, secondary current into 10 power minus 3. So Q is equal to EPA. I mean, the primary voltage can be approximated very close to equal to your induced primary voltage and then primary current to 10 power 3, where P primary and V is voltage, and you can call it voltage and secondary, and I is the current, and the voltage induced in the transformer winding is normally put it EX equal to 4.44 F into pi m into Tx, where X you can be either primary or secondary. Like, so coming to like a typically single phase core type of transformer for output equation, as you can see here with the what we call it the core, that is iron area AI, and what we have a window here with the cross sectional area of AW with the height of HW and width of WW. That's about the width of the window, height of the window, and total area of the window, and cross section area of the core. So these dimensions will be using in this output equation. So the output of the transformer in kVA is related to main dimension, and the output can be determined in terms of area of the core or iron, that is AI, and area of the window AW, and the window space factor KW. I mean, window space factor comes by typically by, because you will be putting some space, not only entire window space for the winding like copper or aluminum, but conductors, but some area goes to insulation. So we account for that, we put called window space factor, and that depends how much insulation depends on the voltage rating also of the transformer. So this KW is also affected by the voltage rating of the transformer. So in case of single phase transformer, there is a one primary and one secondary winding. So half the primary and half the secondary are placed on one limb, and other half of each of the winding is placed on the other limb, and each limb has half the primary and secondary, and hence the total copper area in window is given as AC equal to total copper area equal to primary winding into secondary winding, area of primary and secondary, and that's equal to number of turns of primary, then area of the primary conductor plus number of secondary turns and number of conductor cross of secondary. So that's AC comes TP into AP plus TS into AS. Like, so assuming the same current density in primary and secondary because of similar cooling with the assumptions, so current density we can say will be J equal to normal current density taken ampere per millimeter square. So that will be J equal to IS upon AS, and you can find out the AS means conductor cross section area, primary current divided by conductor current divided by current density, and secondary conductor cross section area, secondary current divided by current density. So now substituting the area and current density in the formula, we can obtain AC equal to TP into I P upon delta and TS IS upon delta. So it comes equal to 1 upon delta, that's a current density in bracket TPIP plus TS IS, and considering the AT as a total magnetic MF, TS IP equal to TS TPIP equal to TS IS equal to AT if we define it. So we can call it the from magnetic circuit AT, and AC can be obtained. So AC can be in AT plus AT divided by delta, of course neglecting the magnetizing current here, that is equal to 2 AT upon delta. So we know that the ratio of copper area in the window to the total window area is the window space factor, which we call it KW. So copper area in window divided by total area, that's AC upon AW. So AC is equal to KW into AW, because AW is a physical dimension. So equating KW and AC, then rearranging it. So 280 upon delta equal to, that's a window total area equal to KW AW, and 80 from this we can find out that is your delta KW AW divided by 2. And now we from going to kVA rating again, output equation Q equal to kVA equal to EP IP to n power 3, we can write Q equal to ET into TP into IP, where into 10 power 3, where ET is the you can call it the volt per turn. So if total voltage of primary divided by total number of turns, that gives you the turns volt per turn here. So you can call it, we are putting just value of EP in terms of ET into TP. Now we can go, of course, substituting the TP IP equal to AT. So here we can say Q equal to ET into AT into 10 power minus 3, and substituting the above equation, the relation AT and the total window area, we get Q equal to ET into sigma KW AW by 2 into 10 power minus 3, and then Q equal to ET into sigma kW AW by 2 into 10 to the power minus 3. And now substituting ET, we can say what is ET? A voltage induced in single turn. It will be Q equal to 4.44 F into phi m into sigma kW AW by 2 into 10 to the power minus 3. So this Q comes because a factor of 2 is cancelled out, so 2.22 F phi m sigma kW AW into 10 to the power minus 3. Now putting the value of typically value of even phi m equal to the Bm into Ai, that is a maximum flux density and area of the core of the area of portion on the winding edge port. So we call it Q equal to 2.22 into F into Bm into sigma into kWai into AW into 10 to the power minus 3. So above equation is the output equation of single phase core type of transformer, and it relates the output kVA relating to its main dimension and parameter, especially the window area as well as the core area, with of course space factor and current density and flux density, current density in the conductor and flux density in the core, and frequency like. So this is, we call it output equation in terms of kVA. Now you can just see how this get modified. Typically this output equation in single phase cell type of transformer, because the arrangement of cell type is there that you have a both the winding on central limb. So both limbs, side limbs use a half the flux, but central limb have a full flux which links both the primary and secondary winding. So you can put how the winding are put. LV is closer to the core and HV again far away from the core, from the central limb. And here of course the difference is that both the windings are wound over the central limb. So each window has the primary and secondary winding, and the total copper area in the window is given by AC equal to TP plus TS that is 2 AT upon sigma into kW into AW, and after solving this we obtain the output equation will be now 2.22 F Bm sigma kW AWAI into 10 to the power minus 3. And of course for going to be three phase core type of transformer, the construction that you have a three limbs, on each limb you have a primary and secondary winding of each phase on this, and cell type of transformer, three phase cell type transformer, you of course have a typically the 5 limbs. So inner 3 limbs you have a primary and secondary like. So now coming to a output equation of three phase transformer of core type, each limb carries both primary and secondary winding of one phase. So in each window there are 2 primary and 2 secondary winding, and there are 2 windows, and each window the total copper area in the window is given AC equal to 2 TPAP plus 2 TSAS. And following the same steps as used, the derivation of output equation of single phase transformer after substituting and rearranging AC equal to 2 TP IP upon sigma plus 2 TS upon is upon sigma, so that come equal to 2 upon sigma in bracket TP IP into T plus TSIS. So now substituting TP into TP IP equal to TSIS into AT, and the copper area becomes AC equal to 2 upon T, AT plus AT, so that's 480 upon sigma, and or you can call 480 upon sigma equal to kWAW, or AT equal to sigma kWAW by 4. So output equation here now becomes 3 into ET TP into IP, that's into 10 power minus 3, so it becomes 3 ET AT into 10 power minus 3. So now substituting for AT and ET, so Q equal to 3 ET sigma kWAW divided by 4 into 10 power minus 4. So now Q equal to 3 into 4.44 into F into phi m sigma kWAW by 4 into 10 power minus 3, and this becomes finally the putting the value of your this, so Q becomes 3.33 F phi m sigma kWAW into 10 power minus 3, and putting the value of phi m which is Bm into Ai, so Q becomes 3.33 F Bm sigma kWAI AW into 10 power minus 3. This is the output equation of the three phase core type of transformer. So here you can call it, we are now relating the window area as well as core area with typically current density and flux density and frequency and window space factor. That's the output equation in terms of kVA. So now coming to output equation of the cell type of transformer, that you have a primary, your LV winding closer to the core and high winding away from the core, special arrangement with the sandwich coil normally on each limb, and as you can see the how the window area is defined typically for each limb here like. So now coming to output equation of three phase cell type transformer, following the same steps followed by earlier, the single phase transformer cell type AC equal to TP into IP upon sigma plus TP IS upon sigma, that's a equal to 1 upon sigma in bracket T PIP plus TSIS. That's you can say TS IP equal to TS IS equal to 80 and AC equal to 80 plus 80 by sigma. So that's a 280S into 280 upon sigma, or 280 upon sigma equal to Kw IW. So 80 becomes delta sig Kw AW by 2. So putting an output equation Q equal to 3P IP 10 to the power minus 3. So Q becomes 3ET TP IP into 10 to the power minus 3. So it becomes typically your 3ET sigma Kw by 2 10 to the power 3, and putting a value of ET, that's a Q equal to 3 point into 4.44 F pi m sigma Kw AW by 2 in 10 to the power. So it becomes like Q equal to 6.66 into F pi m sigma Kw AW 10 to the power minus 3, and finally putting a value of pi m equal to Bm into AI. So Q becomes 6.66 F Bm sigma Kw Ki AI into AW. And typically the rating you can say of transformer per phase given Q equal to Vi into 10 to the power minus 3. So it's a 4.44 F pi m Ti 10 to the power minus 3. So Q becomes 4.44 F pi m 80 into 10 to the power minus 3. So term pi m is called the magnetic loading and 80 called the electric loading. So now, of course, explaining the volt per turn ET we have used in this output equation. So you can call it the magnetic loading phi m Bm into AI give a measure of cross section area of the core, and as the magnetic loading increases the flux density and hence the core loss increases, reduces the efficiency of operation of the transformer. And similarly the electrical loading AT give the measure of the cross section of the winding. So increases the electrical loading, increases the number of turns, resistance, and hence the results in increased copper losses or winding losses and reduces the efficiency. So higher value of phi m and AT will only reduce the efficiency of the transformer, and for economical design the ratio of phi m and AT is maintained constant, which is denotes by one type of the transformer, that is we call it X. So phi m upon AT we take as another parameter in the design, and from which we can get AT equal to phi m upon X, and or X equal to phi m upon AT, or AT equal to phi m upon X. And Q now we can define the output rating 4.44 F phi m AT into 10 to the power minus 3, or we can say Q 4.44 F into phi m square by X into 10 to the power 3, or we can say phi m is under root X into 10 to the power minus 3 divided by 4.4 F into under root Q. Or you can call it, now we can relate between ET and Q. So ET becomes 4.44 F phi m 4.44 F under root X into 10 to the power minus 3 divided by 4.44 into under root Q, or equal to under root 4.44 F 10 to the power minus 3 X into under root Q, or ET is equal to K into under root Q, where the K is under root 4.44 F 10 to the power minus 3 into X. Like. So this gives a relation between the volts per turn to the kVA rating. Now, or you can say volt per turn rating ET equal to K under root Q, where the X and K are constant. Their value depends on type, construction, and service condition. So various values of K exist for the different type of transformer. As you can see here, volt per turn factor here. So single phase core type K varies from 0.7 to 0.85, and three phase core type power transformer it varies 0.6 to 0.7, and three phase core type transformer distribution transformer is 0.45, and single phase cell type is 1 to 1.2, and three phase cell type it is one order of 1.3. So this is the value of the Q which relates between the output kVA rating with the volt per turn, that is E equal to K into under root Q. Now selection of the flux density or magnetic loading in the transformer. So output equation and the EMF equation indicate that the choice of flux density affects the core area AI, and higher flux density reduces the core area. This will reduce the diameter of the circumscribing circle, thereby reducing the length of mean turn of winding. Thus, there will be a huge saving in the cost of copper as well as iron. But a higher flux density by saving copper and iron will also result in increased magnetizing current, leading to the saturation, increased iron losses, requiring elaborate cooling arrangement. So the choice of your flux density Bm also depends on the type and service conditions of the transformer, and it has already been explained that a distribution transformer should be designed for lower iron losses and giving a good per day efficiency, and the distribution transformer comparatively have a lower flux density, and the variation of B depends on the rating of the transformer as a higher value of the for higher rating usually. So you can just see how it is the permissible value of flux density Bm for various type of transformer. So type of transformer like distribution transformer with a hot rolled steel, we have a flux density 1.1 to 1.4 Tesla, and power transformer with the hot rolled steel was 1.1 to 1.5 Tesla, and transformer using cold rolled granted steel up to 132 kVA is a 1.55 Weber per meter square, or for 475 kV transformer 1.6 Weber per meter square, and for 400 kV transformer 1.7 Weber per meter square. So you can see at the typical the voltage rating as well as power rating goes high. So we have a higher flux density used so that the size of the transformer is reduced. Of course, we have to use the better cooling. Now coming to the selection of current density or electrical loading, the choice of a specific electric loading, that is the current density sigma, affects the transformer dimension and efficiency. A higher value of the current density results in a smaller dimension of transformer, but the increased electric loading losses increase the efficiency decreases. So higher value of current density result in a higher temperature rise, resulting in damage to insulation due to local heating, and with improved methods of cooling and with well ventilated winding, the choice of current density is limited by local heating, and the type of transformer affect the choice of current density as the requirement of copper and iron is different in for power and distribution transformer. So the permissible value of current density, that we call it either J or sigma for various type of transformer. So if we talk about transformer standard distribution and small power transformer, the value of current density we take about 1.5 to 2.6 ampere per meter square, considering the natural or air cooling. For medium and large transformers, we have current density order of 2.4 to 3.4 ampere per millimeter square, and large power transformer, it goes with the better cooling, 5.4 to 6.3 ampere per millimeter square. But these are the typical guidelines. You may find with the change of material property and type of insulation, these figures also may go on in higher side also nowadays, typically. Now coming to the design of the core forms the magnetic circuit of the transformer along with the yoke, and the core is built of silicon steel lamination of thickness with 0.5 to 0.5 millimeter with the varnish insulation in between to reduce the eddy current losses and to provide the high resistance for eddy current induced in the core. The core section of a small size transformer is rectangular with circular and rectangular coil, and for higher sizes, circular core with circular coils are preferred over rectangular coils, as the former occupy less space and use lesser amount of copper. The different type of core laminations used for core type and cell type of transformer, as you can see, like EI laminations or double E laminations, double E kind of laminations, or double L laminations, or UI laminations. So these are the type laminations used in distribution cell type of transformer and distribution type transformer. Now coming to design of the core, as the laminated core needs to be used in transformer, a large number of laminations of different sizes are required to be built a circular core. It also becomes difficult to arrange them together to get a circular section. So it is general practice to appropriate a circular core as a stepped core with an infinite number of the steps. So however, the maximum number of steps can be restricted for practical reasons, with the minimum being 1, as a stepped core also enables the use of circular coil, and is also called as cruciform type of core if the number of steps are 2. So you can have a different kind of core type of core, like a stepped core, square core, or rectangular core, and then with more steps, if it is a cruciform, we call it 2 steps, or you have a 3 step or 4 step or higher number of steps for higher rating transformer. So this is the typical construction, you can say how we call it. I mean, the shape of the core have to be selected based on the minimum wastage of the useful space and for minimum length of the copper, as you have a winding, circular winding on the core. So the imaginary circle passing through the corners of the core section is also called circumscribing circle or circumcircle, as you can see in the different type of the shape of the core. So now you can call it influence of diameter of the core is, let us consider the diameter of the core diameter to be d dash d, then the cross section area of the core will be A equal to pi d square by 4. And now volt per ton is already we explained E equal to 4.44 pi m f. So that become 4.44 A into B f, and E is inversely proportional to the typically N V equal to N, and where volt V is constant V, and at the d square N inversely proportional to N. So you can call it that is equal to 4.44 pi d square by Bm upon 4. So here you can call it the volt per ton is increased with the increase in diameter of the typically of transformer core. The influence of diameter of the core now is the diameter of the core is increased, the number of turns in the transformer winding is reduced, reduction of the turns, reduction in the height of the core, reduction of the core legs height, increase in the core diameter, increases the overall diameter and magnetic core of transformer, and increased steel weight, increased core losses in the transformer, and increased diameter of the core leads to the increase in the main diameter of the winding, increases the diameter of the winding turns, reduces the number of turns winding, and less copper in the transformer. So increasing diameter of transformer core, losses in the transformer core will increase, but at the same time losses in copper loss or copper loss in transformer is reduced. So this is typical how you have a different cross section area with the different steps of the lamination blocks here, and how, I mean, this is the basic diagram, and this is how it is the core is there put into the, I mean, like as you can see the photograph, and how the different steps are there in the, you can call it assemble core, like the copper. And this is the type of the core, 3 limbs core, and then 3 limbs with the melted corners. Then you have ideal core with the circular cross section of a power transformer. Such shape will produce a small distribution of the electrical field. More practical core shape is the, for power transformer, the limb is typically made of oriented steel sheets of 0.25 to 0.28 to 0.35 thickness, as you can say stack out is there. So you can call it how the design of the core is. So type of typical limb of the low voltage transformer has a rectangular cross section, and the core is just assembled by I laminations or UI sheets having a standardized dimension. The sheet material may be oriented or non-oriented. The thickness is typically 0.35 to or 0.5 millimeter. The sheets are insulated from each other by a thin insulation layer. A typical filling factor is 0.95 to 0.97 for these laminations. So you can say sheet for a small transformer, as you can see the laminations of so cutting the sheets of a small transformer from a continuous system. The rolling direction is indicated by the arrow, and dimensions are so designed that the stamping produces no leftover parts, like, or wastage is minimum. So cutting steel of how it looks like a small transformer. And then coming to now core stacking factor. So core is primarily prepared by stacking the laminations together, which are insulated from each other by a thin coating or varnish, and assembled core includes the area of insulation also. So stacking factor that relates the cross section with the net core section is defined as the core stacking factor. Net core section AI upon cross section AGI, that's a core KSK stacking factor, and the stacking factor varies from 0.85 to 0.9 because of the insulation put with the different dimensions of the thickness of lamination. So now you can say core stacking factor for square section is net core section divided by core gross section KS factor. So the gross area for square core is AGI equal to A into A, where the, you can say, is the height of the core, and D the diameter under root 2A. So where A is D upon root 2, you can call it what will be the core stacking factor for square wave section, AGI equal to D square by 2 or 0.5 into D square. So net core area stacking factor gross area, so AI becomes KS into AGI, and with the stacking factor 0.9, so AI becomes 0.9 into 0.5 D square, so it becomes 0.45 D square. Now coming to core stacking factor for square core, to determine the utilization of available space in transformer area for circumferring circle is required to be found and given. AC is equal to pi D square by 4 for D diameter, and AI upon ACC is 0.45 D square by pi D square by 4, that becomes 0.58, and AGI upon ACC becomes 0.5 D square divided by pi D 4 is a 0.64. Now you can call it core stacking factor for step cross section area. Why we use stepping cross, that will give you idea. So we have a cross section area given by AG equal to area region 1, as it is mentioned 1 in the inner portion, plus area region 2, where area region 1 is A into B, and area region of 2 is A minus B into B. Hence the AGI becomes AB plus AB into minus B square, or it becomes 2AB minus B square. So now we can calculate for this cos theta, as if we define the angle theta as shown in the figure, A upon D or sin theta B upon D, and A equal to D cos theta and B equal to D sin theta, and AGI become 2 D sin theta into D cos theta, so it be minus D into sin theta square or a square, and that becomes 2 D square sin theta cos theta minus D square sin 2 theta is sin theta square, and AGI equal to D square in bracket sin 2 theta minus sin square theta. So now the maximum area for a given D is obtained when theta is maximum. So to get maximum theta, AGI is differentiated with respect to theta equal to this. So DGI equal to dx, that is D square in bracket 2 cos 2 theta minus 2 sin theta cos theta equal to 0. So theta comes from here. So 2 cos 2 theta equal to sin 2 theta. So theta becomes tan inverse 2. That becomes 31.72 degree. That theta, I mean for minimum, hence the theta 31.72 degree, we get the maximum area of the core for a given D. So now coming to here, A equal to D cos theta will be 0.85 D and B will be D sin theta 0.53 D and AGI will be 0.618 D square and hence net core AI will be A equal to 0.9 D AGI. So AI equal to 0.9 AGI, that becomes 0.56 D square where KI is 9.9. So AC upon AG will be 0.56 square pi D square, that 0.71. So AGI upon ACC become 0.68 divided by a D square divided by D square, that become 0.79. So compared to square wave, we improved to 0.79. And now you can say how it is with the different steps increases, which you can even make a program and get this data. So for this race of AGI to AC or AI to AC or KC, how it become the factor. For square core, if it is a 0.64, then become 2 step 0.79, for 3 step 0.84, and 4 step 0.87. You can see the gain from 0.64 to 0.79 is quite substantial to go from square to 2 step, but that much is not the gain further increasing the. So normally 2 step core are reasonably preferred, but for high rating we go even for high number of steps. You get because more within the same circle you get the more area of the core and you are able to get more output. So now coming to the typically the applied voltage V1 is approximately equal to the voltage induced in the primary, V1 equal to approximately E1 equal to 4.445 M FT1, that is E2 into T1. So number of primary turns you can find out T1 will be equal to V1 upon ET in case of single phase transformer, V1 phase upon ET in case of three phase transformer. Number of secondary turns will be T2 V2 upon ET in case of single phase transformer, V2 upon PH upon ET in case of three phase transformer. So primary current will be your current per phase, that is I1 kV upon 10 to the power 3 V1 in case of single phase transformer, or kV into 10 to the power 3 divided by 3 V1 phase in case of three phase transformer. Cross section area of the primary winding conductor will be I1, A1 will be I1 upon sigma millimeter square, that is A1, sigma is the current density in the primary winding. Secondary winding current will be I2 10 to the power minus kV into 10 to the power 3 divided by V2 in case of single phase transformer, or equal to kV upon 10 to the power 3 into 3 V2 per phase in case of three phase transformer. So cross section area of the secondary winding conductor will be A2 equal to I2 upon sigma in millimeter square. Now coming to some of the objective questions. Magnetic material used in large transformer is normally nowadays we use hot rolled steel. The main disadvantage of cylindrical winding is poor mechanical strength. The yoke with the rectangular cross section area are used in a small transformer. The primary and secondary windings are interlaced in a transformer to reduce the leakage reactance, and primary transformer have a kV rating about typically more than 200 kVA, and cold rolled guaranteed steel has a, you can say, hot rolled steel, all the above like better finish, improved space factor, and much better magnetic property. Typical window space factor is out of 0.3. The various region, the reason for multi-step core used in this to decrease the cost of copper. The tappings of the transformer are provided at the neutral of the high voltage side, and for transformer relation, which type of silicon steel is used, typically cold rolled guaranteed, means all the type. And if the net iron area to 3 steps is 240 millimeter square, the diameter of the circumcycle, by solving this relation, as you can see in numerical, so it comes 20 centimeter. The total copper area accommodated in the window cross section area 300 millimeter centimeter square for a particular transformer, 0.485 times the net area of iron in 200 centimeter square. The window space factor after this calculation comes 0.432. So the cross section area of large capacity power transformer is core section is multi-step, and choice of higher core flux density transformer lead to reduction in overall cost. With the rise in voltage, the window space factor of transformer decreases because of the more insulation, and stacking factor will be minimum for typically for a square type of core. Now coming to some of the numerical problems. For a first numerical 1, for single phase transformer, the distance between the core center D is 0.4 and the diameter of core comes circle D 0.4. To calculate the window width of the window is D minus D, that becomes 0.17 meter. So numerical 2, for single phase transformer, the circumcircle core D equal to 0.2 and distance between the core is 0.64 and the core height is 0.5. Calculate the window area. So that is the solution is window width of the window is D minus D, so 0.64 minus 0.2, 0.44, and area of window is W into SW, typically 0.2 into typically 0.5. So numerical 3, determine the diameter of subcambic circle of the core of 200 kV 50 Hz single phase core type of transformer. It's compressible cruciform core is the distance between the limbs is equal to 1.6 times of the width of, assuming the volt pattern at 14 volt, maximum flux density is 1.1 Tesla, window space factor 0.2, current density is 3 ampere per meter square. Also calculate the width of the largest field. So it comes like volt per turn it equal to 4.45 m and 8 AI equal to 80 upon 4.44. So AI will become, putting the value 0.0573 meter square. And the diameter of the circumference d under root AI upon 0.64 square, that comes 0.324, 0.36, and for the largest stamping equal to 0.85 d, so it becomes 0.72 meter. Numerical problem 4, calculate the diameter of circumcircle of 200 kVA transformer is 6,600 volt by 400 volt, 50 Hz 3-phase core type, like that are assumed as EMF per turn 10 volt, maximum frequency 1.3 Tesla, and density 2.5 ampere per millimeter. So calculate the kVA rating of 3-phase transformer use this step. So given it equal to 10 volt, so AI from this you can calculate, it comes ET upon 4.44 BM into F, getting a value it comes 0.0347 meter square, and diameter of circumference D equal to under root this AI into divided by impact, that comes 0.24 meter. Now numerical problem 5, the calculate the iron area of 400 kVA 50 Hz single phase transformer, maximum flux density in the core is 1.3 Tesla, current density 2.7 millimeter square, ampere per millimeter square, and window space factor 0.25, and ratio of flux to full load MF is 2.4 into 10 power minus 3. Q is given 400 kVA, so BM is given 1.3 Tesla, sigma current density 2.7 ampere per millimeter square, and kW 0.25. So ampere, keeping getting ET equal to ET K under root Q to VA. So value of K can be calculated from these all given value 4.4 F 5 M upon 18 to 10 power 3. So it comes 0.732, and then ET can be calculated by putting the K value and KVA, that comes 14.64 volt, and flux comes 5 M equal to ET upon 444. So it comes 0.066 Weber. Net iron area A 5 M upon BM, so it comes 0.0507 meter square. Now coming to numerical problem 6, calculate the window copper area of 400 kVA 50 Hz single phase core type of transformer, current density 3 ampere per millimeter square, and window space factor 0.5, and full load MF is 0.5 into 10 power minus 3. Also calculate the window area. So given here Q equal to 400 kVA, sigma per 3 ampere per millimeter square, kW is 0.25, loaded MF is 5 into 10 power minus 6. The copper area can be calculated, AC equal to 280 upon sigma. So putting value it comes 0.33 meter square, and kW is so AC upon AW, putting value it comes like your 0.66 meter square. Now there are some unsolved problems. So question number 1 you can solve similar to what we have already covered. Question number 2, 3, 4, 5, and these are the references we followed for developing this material. And thank you very much.